Let's rewind. You've seen this, Pangaea, some 200 million years ago, but we're going way further back to 1.6.
I know there are a series of like supercontinents that come before Pangaea. And I think there's like, Kenor Land, Nuna, Rodinia, and then Pangaea. I think those are the big four, but I'm sure they're gonna bring up some ones that I'm not super familiar with. I think like there's one called just like UR. We'll see.
6 billion years ago.
1.6 billion
big
years
pieces
ago.
of India, Antarctica, and Ukraine were neighbors. So were parts of Africa and South America, Canada and Australia. This is the strange geography revealed by this brand new model of plate tectonics that was released at the end of last year. It spans 1.8 billion years. And of course, here at Howtown, we ask, how do they know this? You know, how did they come up with this model? How do they know where all these continents were a billion years plus in the past?
Okay, yeah. So that's so cool because it seems that that's like a really recent paper, and plate geology is constantly evolving, so we're getting a better and better picture of like where these continents used to be, all of that sort of stuff. So one thing that I am curious about, since it only goes back 1.8 billion years ago, I'm curious what they're going to do for the rest of the 4 billion years, because I know there is some data from back then. The main way that they figure out where continents used to be is based off of some magnetic data. Yeah, so one of the main ways they determine this is based off of the angle at which the magnetic minerals within, a lot of times it's usually like volcanic deposits, is angled, especially compared to all the times it's been deformed, because the ideal for rocks is original horizontality. It's not true for all types of rocks, and there's like specific context, but the default for most types of rocks is that when things are deposited, they are deposited roughly flatly compared to the surface. So you have layer after layer after layer after layer, and depending on the orientation of some of those magnetic minerals within some of those rocks, you can piece together at least where those magnetic minerals are compared to the pole. Because whenever, like, imagine it's like an igneous rock, whenever those minerals crystallize, usually, at least there's a portion of them that are oriented towards magnetic north and south, so they're pointing in alignment with that. And depending on, and since the north and south are relatively consistently at the poles, even though the poles switch every once in a while, even though they are relatively consistently at the poles, depending on the angle, you can kind of figure out, like, okay, so the angle in this part of the rock record is this way, and then the angle this part of the rock record is this way, so it's likely that this continent moved in this direction. And you can figure out a ton of data, and if you tie all of those things back, you can actually reconstruct previous supercontinents. It is amazing, like super cool research, and I'm very excited to see how they cover this.
So to find out, you and I are going to hitch a ride on 2 of these continents. I'm going to drop you off in Canada near some of the oldest rocks ever found. And I'm going to start
Australia?
on the other side of the world in Australia.
Yeah, so the reason that they're choosing Canada and Australia, because these are, at least to my knowledge, like the oldest continents that are out there. So there are parts of Australia that we actually use to date zircon. When we are trying to figure out how old the Earth is, there are minerals called zircons. These have a ton of radioactive elements in them that we are able to date and give us a time scale for how old the Earth is. It comes out of the Jack Hills, I believe, in northwest Australia, which is a formation that's somewhat more prominent in like northwest Australia. Basically, the thought with those is that those are the oldest datable material that we have. And it's a relatively decent way to like to think of like, oh, when these minerals crystallize, these were probably at least some of the first minerals to crystallize. And since we date them, we are dating basically the age of the Earth crystallizing, which is really crazy that these are found specifically in Australia. And there's also a very old series of rocks, I believe, up in like Greenland and up in like what they call the Canadian Shield. So imagine like northern Canada. Each of these areas are some of what we call like the Earth's very first cratons, which is like stable interiors of continents and some of the first like continental crust, or at least what we think is. So, and especially compared to places like Florida, and compare the age of these places to places like, a better example of something that would be way younger is something like Hawaii, which is just like a huge pile, like a mountain of basalt, and then these rocks closer, like an order of magnitude older. So things that are like 3, 4, 4.5 billion years old.
We'll ride these patches of crust into the ancient past, and along the way we'll dig up some of the clues that scientists use to map a world that no longer exists. Our journey will span 4 billion years. Every pixel on this timeline is 3 million years, and this tiny fraction of this pixel contains all of human civilization. Okay, let's start rewinding. We'll give each region its own color so they're easier to follow, and we'll get rid of the ocean so we can have a better view. These are tectonic plates. They typically have some dense oceanic crust and lighter continental crust floating on top of the softer solid mantle. Just 65 years ago, most scientists didn't accept plate tectonics. People really didn't think this was happening.
I would have thought this would have been back in like the 1700s that somebody came up with this. But this was in people's lifetimes that are still around.
Yeah, totally. One of
like geology and planetary science are accelerating rapidly, and how we are able to understand how the Earth evolves over time. Like some stuff we still really don't understand are things like earthquakes and volcanoes, and that's something I hope within my lifetime that we get some ability to like predict volcanoes and earthquakes, just so we can predict population centers better. Because places like San Francisco or a lot of places in like Japan, are very, sometimes they'll receive like huge earthquakes, and we just don't know how to like predict those super great.
One of the first clues that this is happening is just looking at the continents, and this map was one of the first that showed semi-accurate outlines. Its creator, a Flemish cartographer who definitely could be played by James Cromwell, noticed that Africa and South America looked like they had been torn apart. Over the centuries, a few other people noticed the same thing, and other odd clues started piling up. Old shark teeth were unearthed high in the Alps. Identical plant fossils were found spread across different continents. Some people suggested that maybe land could rise and fall, connecting continents and creating new oceans.
Yeah, so the specific plant that they're talking about there, I believe, is Glossopteris, which is like a type of fern. And it's kind of weird because one of the things that was very confusing to a lot of people who were doing some like Antarctic expeditions is that they would find plant fossils in Antarctica, which is just like this frozen wasteland almost. So it's like, it's really crazy to like be able to piece these things together, especially like when you're a scientist doing research, because it's like a hint at like a deeper like reality. Because I imagine it would feel like very strange to find these things, and it would be fascinating because it'd be like a hint at a deeper reality that we just like don't understand yet. A place for discovery and an expansion of human knowledge. So it's always really cool to like talk about like this history aspect of like how scientists came to understand the world as they do today, because sometimes it can tell you about what kind of things and expanses and what the process is like for seeing future increases in our understanding.
But in the 1910s, Alfred Wegener proposed a different theory. The continents were drifting.
Yeah, so this guy got clowned on so much because of this idea. It is like actually crazy how much like geologists back then hated him. And the main reason is because he did not have a mechanism. He didn't have an idea for like what could be causing like these huge like chunks of land to be like moving. Like some of his thoughts were like, oh, maybe the tides do it, which is definitely not true. But he pioneered the idea, and geologists also didn't trust him just because he was more of a climate scientist and less of a geologist. So it's just like, oh, of course this guy would try to think that he knows what's going on with geology, but he happened to be right. And they actually found evidence of people like Marie Tharp and some people who measure like satellite data, and much later, like in the 90s, and obviously like fossil data, and people who measure do like satellite data now can actually measure the rate of drift, and it's like, oh, it's like about as fast as your fingernail grows. Very cool.
If you smushed all the continents together in what is now called Pangea, those identical fossils matched up perfectly. Other scientists didn't buy it, though. For decades, they called the idea a fairy tale.
Yeah,
What was
people
keeping the scientific
hated
community
it.
from acknowledging the possibility of this? Like, what's the big holdup?
It's funny because he was a meteorologist. He was working in a field that he wasn't brought up in. And I think that was an advantage for him because everyone else immediately encountered the problem. Well, how would this even work?
The mechanism.
Incorrectly thought that Earth's rotation might be causing the continents to plow through oceanic crust like ships through ice. But physicists and geologists knew that those forces and the rock itself weren't strong enough for that to work. They really wanted more proof and a better mechanism, and they were about to get both. Sonar gave us a new way to scan the ocean floor, and in the 1950s, Marie Tharp spent years at the drafting table translating this kind of data into incredibly detailed maps. she would hand draw these. I mean, it's kind of incredible.
Wow.
It looks like the map in the
That's
back
crazy.
of Lord of the Rings.
She noticed what looked like a long trench in the middle of the Atlantic. It stretched all the way up to Iceland, and you could actually see where it splits this valley. She pointed
that's
this
so
out to her
cool.
supervisor, and he was like, that's just girl talk. But eventually, he published the findings under his own name. Jacques Cousteau was also skeptical at first, so he dropped a camera into the middle of the Atlantic, revealing pillows of lava newly extruded from the center of the Earth.
It's because you have, an eruption under the sea. You sort of need to prove that the plates are actually moving. Volcanoes erupt in Hawaii too, but that doesn't necessarily prove plate tectonics.
They needed more proof that the ocean floor was spreading, and that proof came in the form of a miraculous little mineral called magnetite.
Ooh, has a cool name.
It's this iron-rich mineral, and
Okay, I know what they're going to talk about here, and one thing that's really fun is like as this stuff. When you're at a plate boundary, like the mid-Atlantic spreading center is what they call it, one thing that you see is like the magnetic minerals, and they're going to talk about this as like magnetite. So like the one thing that's fun about Earth is that its polarity changes. So I believe right now the positive end is in basically like imagine like somewhere close to the North Pole. The negative end for like the Earth's magnetic field would be closer to like somewhat imagine like the South Pole. So if you take a compass, it's like, okay, so it's pointing north towards the North Pole, south towards the South Pole. Occasionally what you end up happening, and we still don't understand exactly why it does this, but the magnetic fields flip, right now you have the positive end up towards the North Pole, you would have the negative end up towards the North Pole, so you have that flip, and then every once in a while it flips back, and then it flips. What's fun about this, and why this is important for what we're specifically looking at, is that these magnetic minerals, when they first are extruded from the crust at these spreading centers, through what we call like decompression melting, so basically what's happening is Earth has like a conveyor belt of this stuff that used to be solid, but since as it gets closer to the crust, it becomes less and less pressurized. As it becomes less pressurized, it turns more into a fluid, more into like a magma, and then if it makes it to the surface of that ocean, because a lot of times it just starts to crystallize, as soon as it gets close enough where water can interact with it, which is usually a little bit below actually directly interacting with water. But this magnetite, as it comes out of the spreading center, locks in the polarity of the Earth. And if you look through the different sequences as you go away from the spreading center, it'll be oriented in one way, and then oriented in another, and then oriented in one way, and then oriented in another. And that can give you a time scale and allow you to reconstruct how fast the spreading center is moving over time, especially when you control it for each of the pole flips.
When it's hotter than about 580 degrees Celsius, it's not really affected by Earth's magnetic field. But as it cools, it locks into alignment with that field and stays there.
It's like a built-in, burnt-in compass mark inside the rock.
Exactly. It's a compass that captures that moment in time. And it turns out that over time, Earth's poles switch places at irregular intervals. And you can see that switch in the ocean floor. The magnetite points north, then south, then north again, and so on, providing proof that the seafloor was spreading. But they still needed to explain what was causing the movement of the plates. Can you guess what the early theories were?
I mean, is it like little bath toys kind of just bobbing up and down on a sea of hot magma?
Yeah, I mean that is sort of what they were initially thinking. So the mantle isn't this ocean of molten rock. It's mostly solid. It can still flow over millions of years, but it looks like these currents have only a tiny effect on plate movement. Instead, they're pretty sure the main driver is what's going on at the other end of the plate. In subduction zones, the densest oceanic crust sinks into the mantle and pulls the rest of the plate with it.
Yeah, so they call this slab pool, which is always really fun. In structural geology investigations, sometimes they can kind of figure out whenever there's like the end of a slab pool or a slab pool starts slowing down. It's really crazy
You
stuff.
actually are like tugging the conveyor belt of the continents behind you as you sink.
Yeah, that's the main force, they think.
Yeah, what kind of scale of movement are we even talking about here? Like the fastest moving plate on Earth. Like, how much is it moving in a year?
To help answer that very question, NASA sent up this satellite in 1976.
Well, it was the 70s, so of course it had to be a giant disco ball satellite.
They bounced lasers off all these reflectors to measure how much the continents were drifting. And they found, for example, that North America and Europe are moving apart at a rate of about 2 to 3 centimeters per year, And the fastest plate, the Pacific plate, is going 7 to 11 centimeters a year.
Wow, slow down, buddy.
Carl Sagan placed a plaque inside the satellite that showed Earth today and Pangaea 268 million years ago. This arrangement of Pangaea makes sense if you look at the age of oceanic crust. Red is the newest rock, blue the oldest. Rewinding so that newer crust disappears back into the mantle, we can follow how the plates must have moved. And Pangaea is where we find ourselves now. We've zoomed past a bunch of stuff. This is before mammals. There's not even dinosaurs yet.
Oh, wow. We skipped a lot of cool chapters of the book here. Okay.
Because there's so much more to go. I mean, we're going to go 4 billion years in the past. We're only like 300 million right now. Oxygen is thicker. We're surrounded by giant insects and the ancient relatives of amphibians. And
Carboniferous. Ton of coal
It's way
being
harder to
deposited
map the
then.
world before Pangaea. For one thing, hardly any oceanic crust survives from that time, so we can't rely on that. But luckily, there are other hidden clues. We'll get to that in a second, but first I want to thank today's sponsor, Storyblocks.
Storyblocks.
When I was making my last episode, I wanted to do a little scene where I represented all of the journal articles that I read by having them sort of rain down. So I was gonna ask my wife to like drop them from a ladder or maybe like hide and
I'm
throw them
gonna
into the air.
I was wondering.
I'm gonna skip past that.
You're on La Russia right now, which formed when your bit of Canada crunched into part of Europe about 400 million years ago. That series of collisions created a long line of mountains, and we can still see them today spread across continents.
How do we know that those mountain ranges used to be the same mountain range if they're spread across
This is
the
a great
globe?
question. One thing, they all look like they're made from the same kind of rock, but they can also tell that they're the same age. Over on Joe's channel, we explain how scientists figure out when rocks formed. It's a technique called
Zircon dating.
You can see the
Yeah,
whole
yeah, yeah.
explanation and Joss and I forming a crystal lattice over on Be Smart. Zircon dating helped scientists figure out that these separate mountain ranges used to be one.
Made of the same stuff, cooked at the same
Mm-hmm.
time, probably not a coincidence.
As we speed into the past, it's getting a little lonely because animals and plants are devolving back into the ocean.
It's a barren wasteland. Okay, got it.
And on top of that, oxygen levels are dropping. The model shows that a lot of the continents have drifted closer to the South Pole, and you're now near the equator. In Canada, they actually find hot...
Okay, we're about to hit one of my favorite events in like all of geologic history, which is the I think it's like snowball Earth or slush ball, some people say, where you just have a lot of it, like a vast majority of the Earth is just like covered in a huge fucking series of glaciers. So I'm excited to hear how they talk about
water
that.
corals left over from this time.
That's a
Tabulate
picture
corals.
of a fossilized like coral reef. That's super cool.
Tabulate coral.
Meanwhile, in what is now Morocco, we find the remains of only cold water species. But there's actually a more precise way to tell that Africa was once near the South Pole. And once again, it's magnetite. When they find these little frozen compasses on continents, they seem to tilt in wildly different directions as you move back through older and older rock.
Yeah,
This
yeah.
makes sense.
That's what I was
if
talking
the
about
continents
earlier.
are moving relative to magnetic north. And you can use this to reconstruct their positions so they're always pointing towards the same pole. Paleomagnetism is one of the most important tools in building a model like this. It should be said that it's not like the silver bullet. These dots are points in time when we have data
There are
from
huge
magnetite
error bars
for
on
different
that.
chunks of crust. And there are big gaps. As we move backward in time, uncertainty increases, and so does danger. We need to strap on oxygen tanks now because the microorganisms in the sea aren't pumping out enough oxygen for us to survive. And things are getting icy. Look at this photo from Norway. In the lower layer, you can see lines scratched into the rock by ancient glaciers. And then in the top layer, you can see the stones and sediment that those glaciers left behind.
Yeah, so they call this a glacial tillite, or like usually what they call this is generally like, I think it's like a tillite. And one thing that's fun about them is that they are poorly sorted. So, and I'm a sedimentologist, so this is like one of my focuses, although not specifically on glacial stuff, is that they're poorly sorted. And what they mean by whenever they say poorly sorted, that means that you have small specks of mud right next to huge like fucking like boulders, larger rocks. And that you take a look at these things and they're all just like smashed together, because when ice grinds a bunch of stuff together, it just tends to dump it all off in a very unconsolidated way and deposit it in a way that looks like this. And this is very distinctive. Whenever you see this, they're like, oh, okay, there's probably a glacier or some ice or something that's causing this really like particular rock type to show up. So it's always really fun.
In many places, those glaciers seem to have scraped away eons of rock. Then the glaciers
it's really
retreated,
sad.
and new layers were added, creating this big age gap. You can see this in the
Great
Grand Canyon, where there's a jump
unconformity.
of over 1 billion years. Some people think that during this time period, most of the globe was covered in ice, with a belt of water in the middle. We're now 780 million years in the past, and we've joined the supercontinent of
Rodinia.
It's got pieces of
Yeah.
most of the continents. So
Love
the
that
gang's
one.
all here, but they're all scrambled up.
Quite jumbled. All right. I'm nodding because I'm taking your word for it, but inside this is like very hard to believe.
I mean, it is hard to believe. It's hard to believe that things made a journey this far. I mean, the paleomagnetism is a big help in sort of proposing where things were, but then they find these other clues, like there are layers of rock in the Grand Canyon from this time period that perfectly match up with layers of rock in this outcropping in Tasmania, which suggests that they were both once part of a shallow inland sea that formed right here. It's still worth noting, though, that this configuration isn't certain. This is one recent model, but of course there are other scenarios that people have proposed. And it's also hard to say exactly what Rodinia was shaped like. These chunks of crust could have been warped in different ways, extending the coastline or leaving gaps that would have been filled by ocean basins. Over the next hundreds of millions of years, we'll float apart and then come back together again.
We needed to do our own thing for a while, but we're coming together.
Yeah.
We're coming back together.
This new supercontinent is called Nuna, or Hudson Land,
Nuna.
or Columbia, depending on who you ask. And this is one of those moments where, again, you can see the rocks. There's part of Queensland that looks exactly like the rock up in this part of Canada. And so they think that it just formed, broke off, and drifted over and became part of Australia. So this piece of Canada is still in Australia today.
Okay, that is actually crazy. You just had like a piece of Canada rip off and then become part of Australia, especially, given like how far they are from each other today. That's always, wow.
Farewell gift.
No matter where you go, part of me will be traveling with you.
When we're going this far back, like, are there the same number of tectonic plates as there are today? Or do these things like hook up for a little while and you get new ones breaking off?
Yeah, I mean, it's always changing. So yeah, there's not the same number of tectonic plates. You can see over time new cracks forming, others closing. What is maintained is the cratons. So these chunks of continental crust that are part of the plates that have persisted to this day. Canada is made up of a bunch of different ones that are all kind of mushed together. You can almost imagine like chunks of clay that are slowly being added to create what is now Canada. Australia is the same deal. Both Australia and Canada have some of the oldest cratons. Even though they're going to drift further into the past, it's probably not safe for us to stay on them any longer. So I think we gotta hop off the crust, watch from a safe distance. Over the next couple billion years, these cratons are going to probably spend some time under the ocean, under other rock, so it wouldn't be a good place for us to stand. In the deep roots of some cratons, diamonds are forming, and so where these oldest bits of crust ended up is where most diamond mines are found today.
Yeah, that's also true of some types of metals too. Like I believe, I'm trying to think. I know a lot of gold mines are concentrated in certain parts of Australia that tend to be like Precambrian. A lot of places in Africa very good for like cobalt, things like nickel, heavier elements. Generally.
Below us, cratons are melting back into the mantle, but a few remain, including the Kopval craton from South Africa and the Pilbara craton from Australia. And because of the kind of rock that they're made of, scientists think they might have formed in a similar place and been part of maybe another continent that they cleverly called Volbra.
It's a celebrity couple, but it's cratons.
They both have these weird little spherules. Do you have any guesses about where these might have come from?
How far back in time are we now?
This is 3.47
Oh, is this like
billion
some of the
years
first
ago.
life?
If I remember right, like life is starting to happen.
It's like little
around this
like
time.
bacterial mats.
That's a good guess, but these are unrelated to life.
Oh, okay.
turns out.
Oh, darn.
Damn.
These actually come from a meteor strike. So a meteor hits, it liquefies the rock, and it splashes up in this little spray that cools into these little marbles.
That's
essentially.
horrific. That's so violent. Like for something to hit so hard that it melts the earth into glass droplets.
And that violence is becoming more common. We're getting hit by quite a lot of meteors. And the best evidence for this bombardment doesn't come from Earth, it actually comes from the moon. Here you can see one of the moon's giant impact craters. Apollo 15 visited its rim and grabbed a chunk of this rock. It turned out to be 3.8 billion years old, and it carried all the signs of being shocked by an impact. A bunch of other lunar samples also support this idea that there was a spike in meteor strikes around this time.
So those marks have been left on the moon because the moon doesn't have tectonic plates. But are there any craters left on Earth?
The Earth is too alive and vibrant for something like that to stick around.
Whereas the moon is just a scarred husk of violence that records every punch it ever took.
By now, all of the cratons that we've known have disappeared. They don't exist.
Yeah, by that point you just get into like the pre-tectonic regime, like Earth before it really had like continents or like ocean beds. Really crazy era that we still don't really understand that much. Things like I believe this is like you're in the Hadean or maybe like the very, very early Archean.
Yet. But somewhere down there in the crust, a very special rock is forming. This rock will survive to the year 2025 and be held by Joe Hansen.
This is the rock that hadn't been recycled down into the Earth and messed with by chemistry.
And now scientists are studying this rock to learn more about Earth's infancy.
Now I can look at that rock and say, I know when you were born. I know your whole life.
The world is now new, and there's a mess wherever you step. So let's reverse course and watch the planet churn back towards the present.
It really extends your idea of the living world. Earth is not just like a canvas that stuff is painted on.
Plate tectonics built the shallow seas that cradled the first life, and then shattered that nursery into 1,000 niches where new creatures would have to adapt and evolve. And the process isn't done. This is the final image that Carl Sagan smuggled aboard that disco ball satellite. It's what we think the Earth will look like in 8 million years, transformed once again. Howtown is just 3 people, and we could really use your support to keep on.
Okay. Well, that was very good. Super good coverage and very high quality video. I really enjoyed that one.